Let us begin with the bug that decides whether this design is safe. At gate A, one car drives towards the entrance. Almost at the same time, a second car approaches gate B. Inside the lot, there's only one free medium spot, M13. Now look at the software. The first version normally has two lines: find an available medium spot, then assign the car to it. The lines look harmless, but watch both threads stop between them. Gate A finds M13 free. Gate B also finds M13 free. Both threads are holding the same answer. Gate A assigns its car. A moment later, Gate B uses the spot it selected earlier. Now two drivers have been sent to the same physical slot. So the real problem is not only finding a spot, the complete allocation must behave like one atomic operation. First, find a compatible free spot. Second, claim that exact spot for this vehicle. In the same protected operation, decrease the available count for the matching floor and spot type. Then create the ticket that records which vehicle received which spot. All four steps must succeed together. Otherwise, another gate can see a stale count, or the system can occupy a spot without producing the ticket required to release it later. Keep this four-step critical section in mind. We will build the design around it. Before writing classes, follow the business journey. A vehicle enters, the system allocates a compatible spot, it issues a ticket. Later, the ticket comes back and the same spot becomes free again. These verbs give us the life cycle. Now add the constraints. The lot has several floors. Spots are small, medium, or large. Entry and exit gates work concurrently. Availability is shown per floor and per type. And the allocation rule may change from one parking site to another. The nouns suggest parking lot, parking floor, parking spot, vehicle, and ticket. Now focus on the changing allocation rule. That requirement gives us one more abstraction: parking strategy. The strategy box appears only now because the requirement has justified it. We did not begin by forcing a design pattern into the model. Give each class one job. The lot coordinates the use case. A floor owns its spots and availability. A spot protects one occupant. A vehicle describes the spot type it requires. A strategy chooses according to policy. And a ticket records one active parking allocation. Now we will type code, but not from the top of a file. We will type the block that the design needs next. Spot size is a fixed set, so start with a Java enum, small, medium, and large. As soon as this enum appears, the garage can group spots without relying on fragile strings. Next, define the minimum vehicle contract. Every vehicle has a plate and tells us the spot type it requires. A car returns medium. Motorcycle and truck follow the same contract, so there's no need to watch us type the same idea 3 times. Now type the most important entity, parking spot. It owns an ID, a spot type, and one optional occupant. Is available checks whether the occupant is empty. Assign rejects a second vehicle. Release rejects an empty spot, returns the old vehicle, and clears the occupant. Watch the consequence. One assignment succeeds. A second assignment is blocked by the spot itself. Then release returns the spot to the free state. This is a useful low-level design rule. Put the invariant beside the state it protects. Suppose parking lot stores 2,000 spots in one flat list. To answer a request for a medium spot, it may inspect small and large spots that can never match. The same scan is repeated when a display board asks for a count. A floor is the natural owner of this information. Type 2 enum maps. The first groups spots by spot type. The second stores the free count for each type. Now, a medium request searches only the medium bucket on that floor. Be precise about complexity. Selecting the first free candidate may still scan the medium bucket, but the displayed availability count is now constant time. Read one integer from free count. We are not going to call a list scan O of 1. The floor must update the spot and the count together. On assignment, it first delegates the state change to the spot. Only after that succeeds, it decreases the matching free count. On release, it first clears the spot, then it increases the matching free count. Finally, it returns the vehicle that was removed from the spot. The availability board and the real occupancy now have one owner and one consistent update path. The same garage can use different allocation rules. An airport may choose the nearest floor, a mall may spread cars across floors, an electric vehicle garage may prefer a charger. The domain objects are stable, but this rule changes. If we put every site rule inside park, the method becomes a growing if-else chain. Each new policy forces us to reopen the core workflow. So type a small strategy interface. It receives the floors and the required spot type and returns an optional spot selection. The selection contains both the floor and the spot because both are needed when we update availability. For version 1, type only nearest first strategy. It checks floors in order and asks each floor for a compatible free candidate. The first match is returned. Later, a different strategy can be injected without changing parking lot, parking floor, or parking spot. Before we return to the race, type the allocation record. A ticket stores its ID, vehicle, floor, spot, and entry time. It is not just a receipt, it is the information required to find and release the same allocation later. Now the parking lot can become the facade. It owns the list of floors, the injected strategy, a map of active tickets, and one re-entrant lock. It does not own every spot directly. It coordinates the classes that do. Return to park. First acquire the lock immediately before the critical work. Then enter the try block. Ask the strategy for a selection. Let the selected floor assign the vehicle and update its count. Create the ticket. Store it in the active map. Return the ticket. In the finally block, always unlock. Now replay the two gates. Gate A enters the critical section first. Gate B must wait. By the time Gate B is allowed to search, 1M3 is already occupied, so it receives a different spot. The lock covers selection, claim, count update, and ticket creation as one consistent operation. A single lot-wide lock is simple and correct for the first version. It also serializes every floor. At much higher traffic, we can split locks by floor, but then the strategy must recheck the candidate after acquiring that floor's lock. Start with correctness. Name the scale path separately. The exit path is the reverse lifecycle. First, lock the lot. Remove the ticket from the active map. If no active ticket exists, reject the request. Ask the ticket's floor to release the ticket spot. The occupant leaves. The medium count increases. Because the ticket was removed, it cannot be used a second time. In the finally block, always unlock. Now a new requirement arrives. The entrance board, mobile app, and analytics all need availability changes. Direct calls from parking floor to every screen would mix display code into the parking domain. This requirement forces an observer seam. Type a small availability listener interface with one on-changed method. After a sign or release, the floor publishes its number, spot type, and free count. Listeners decide how to display or record it. Factory has a smaller role. If an entry adapter receives only vehicle type and plate, a vehicle factory can create car, truck, or motorcycle in one place. But if callers already provide a vehicle object, do not add a factory just to mention another pattern. Now the completed code blocks can become the class diagram. Parking lot contains floors and a floor contains spots. A spot may hold one vehicle. A ticket records the vehicle, floor and spot. Parking lot uses a parking strategy, while availability listeners stay outside the floor. Now read the arrows carefully. Lot to floor and floor to spot are composition. They form the physical structure. Spot to vehicle is a 0 or 1 association. Car is a kind of vehicle, so that is inheritance. The strategy is injected and swappable, so it is a dependency. Now the patterns have reasons. Changing allocation policy gives strategy. Repeated input to subclass construction may give factory. Several independent availability consumers give observer. Patterns are consequences of change, not decorations on a diagram. Finally, test the design. Add an electric vehicle first strategy, a new display listener, or a billing calculator at exit. The core spot and parking workflow do not become one giant class. That is the real extensibility check. One final boundary. A Java reentrant lock protects one process. If two application servers manage the same physical lot, each server has its own lock, so the atomic claim must move to shared storage. For example, a database transaction can lock the selected spot row. The critical section stays the same idea. It moves to the place every server can see. This design is also bigger than parking. A meeting room, locker, connection pool slot, or thread pool worker follows the same shape. Match a request, claim one resource, issue a lease or ticket, and release it later. Remember 4 rules. First, let the write object own mutable state. Second, index availability where it is used. Third, inject the matching policy. And fourth, make selection plus claim atomic. That is parking lot low-level design, built from real pressure instead of a pattern checklist. Find deeper engineering guides and role-specific career paths at crackingwalnuts.com. Follow Cracking Walnuts for the next visual breakdown.